All right, silly people, here's the situation. We're going to be using the matplotlib imshow function to display the electric potential due to a couple point charges that are 10 centimeters apart in a 1 meter by 1 meter square plane. Um, so this is a pretty complicated little problem that we've got going here, especially part C, because it's going to involve calculating potential from a surface charge density. I hope to goodness your professor isn't assigning that part of the problem, but I'm going to do it anyway. Um, but first of all, we have to do these first parts, which is just the point charges. So um, we're going to do code cell here. So that is going to be, we're going to be importing numpy as np as always, and then also matplotlib.pyplot as plt. We're going to define some physical constants first. So for the point charges, we have a couple of guys that both have q equals 1 c. So we're just going to do q equals 1. We have epsilon naught in the phi equation, so we're going to define that. So epsilon naught, which I'm going to call E0 and in this code, is a 0.854 e to the minus 12. And then the size of the box is 1 meter. The distance between the 2 point charges is 10 centimeters, so let's call that d equals 0.1. To calculate the potential at every point in a array, pretty much, we do need to know what the positions of those 2 points are and define them. So x1 is going to be the x position of the particle that's on the right. That's going to be the one that's going to be positively charged in my solution of the problem. So that's going to be the length of the box plus the separation between the 2 particles divided by 2. Similarly, the position of the negative particle will be L minus d over 2. We're going to have them both be centered in the plane, so it's going to be y1 equals L over 2 and y2 equals L over 2, but you can, of course, change that for other problems if you want. We're going to do a grid of 100 points. As per the suggestion here, he does want us to calculate the potential at 1 centimeter squared spaced points. So 100 is going to be how many we need to do. We can create an output array, which is going to be a numpy.empty with the shape of n plus 1. It is n plus 1 because it has to include the x equals y equals L points. So it has to be that specific shape. So you can index up to there, and that's n plus 1. The data type will be for floats. And so now that we have all those, we can actually get into the loops that we're going to be doing. So for I in range n plus 1, we need to be able to get a y coordinate that is being represented by the I that we're using. So because, again, because y is the vertical position on the field, so up and down, and the array index I represents what row you're on, I is matching up with y instead of I matching up with x, which is what you would think, but not this time around. So the separation between each of the grid marks that we're going to be looking at is the length of the box divided by however many slices we're doing. So the y coordinate for this is going to be a times I, right? And then we can loop over j as well, n plus 1. And here we can say x equals just a times j, right? We do need to calculate the distance between the point we're evaluating at and the 2 different point charges. So that is going to be done by Pythagorean, I can never say it, Pythagorean theorem, which is the square root of the x difference squared plus the y difference squared, right? R2 will be identical to that line, so let me just copy it down, but replace all the ones with 2's, obviously. So we do want to be able to catch singularities right away, so I'm going to create a couple of conditional statements. If the R1 ends up being 1e minus 12, which is less than 1e minus 12, which just means it's an arbitrarily small distance between the grid mark and the source charge R1, then that means that the grid point we're evaluating at is essentially on that grid mark, so we can just set what the phi value is to an arbitrarily large number here. From us, I can just set it to 1e12 and be good. Same thing for R2. If it gets arbitrarily small, we can set the electric potential to be arbitrarily large, but in the minus direction because it's a negatively charged particle. That way, whenever we make the graph, those points don't represent anything physically, but it will make the graph look nice and smooth whenever we apply the color map, right? So otherwise, we use the electric potential formula, which is given up there. It's Q divided by 4 pi epsilon naught R. So I'm going to group the prefactors together. It's actually Q divided by 4, and then let me put this in parentheses, 4 times numpy's version of pi times epsilon naught, but then also times, we're going to have to split it up into R1 and then R2. The R1 has a positive Q and the R2 has a negative Q, so we'll do 1 over R1 minus 1 over R2 there, right? After all is said and done, we can go ahead and use the imshow function, mapping out phi. We are going to have to pretty stringently set the Vmax and Vmin arguments here. So for our purposes, 5e10 is a good Vmax for this, and Vmin equals minus 5e to the 10. That way, if a value gets too high or too low, it just won't show up on the the plot, and then the other colors around it will change to fit those maximum and minimum values. And so the color map that we're going to choose, so CMap argument in here, I like the jet color map for this one. So let's give this a run, see what it looks like. And it looks fantastic. There's the positively charged particle on the right, negatively on the left, and then 100 grid points on the 1 meter scale to, differentiate how, like what the potential values are at each spot. So that's pretty cool. The next part is to also calculate the electric field components at each of those grid marks. So electric field is a negative gradient of phi. So that means we're going to be doing partial derivatives with respect to x and y, then flipping them, so minus those derivatives for each of the grid marks. So let's create a couple more output arrays, ex. Since we do, I'm going to end up using the quiver function from matplotlib to show this, and that takes in an x array and a y array. So that's why I'm doing ex and ey. They're going to be the same shape as our phi output array. So n plus 1 here with data type float, and again, EY is going to be the same shape, but what we're going to do with them is going to be different. So for I in range n plus 1, in this loop, we're going to calculate what the EX values are. We're going to have to create a separate loop for the EY values. So this is going to be for j in range n plus 1, for I in range 1 n. Different loops for different arrays. Right in here, we generally want to use the centered difference formula for calculating derivatives numerically, except we're near on the edge of the potential. So if you try and do a centered difference with I equals 0, so you're all the way down, or you're all the way up here, or I equals 100, so you're all the way down here, you're going to end up with errors because the I plus 1 guys don't exist anymore. So instead you want to do non-centered differences on the edge marks, and you want to do those right here. So EX indexed I comma 0 will be calculated with a centered off-centered difference derivative. So this is going to be phi I comma 0 minus phi I comma 1 over A. Again, since the electric field is a negative derivative, I had to flip the order of those. If it was a positive derivative, then it'd be 1 here and 0 here, but it's negative, so that's how we did it. Also, the bottom wall, so EX indexed IN, has to be calculated like this. So phi I comma n is less than phi, or minus I comma n minus 1, and all divided by A. Right? Cool. But then in here we can just do a centered difference formula. So EX I comma j will be phi I, it's just going to be j minus 1 here, minus phi I j plus 1, and it's divided by 2a instead of a because it's a centered difference again. So that's good there. We can do the EY in much the same way. So this is going to be EY indexed just 0 comma j, which is going to be equal to phi 0 comma j minus phi 0, or actually 1 comma j here, divided by A. EY then of n and j is equal to phi, again indexed n comma j minus phi indexed just n minus 1 comma j over A. So yeah, so if it wasn't clear, these are coming from derivatives with respect to x. On the scalar potential, these guys will come from derivatives with respect to y on the scalar potential. So that's why it's split up into x and y again. This guy will be phi indexed I comma, and then it's the I thing that we have to change this time, not the j one. So it's going to be I minus 1 j minus phi indexed I plus 1 comma j, all divided by 2 times A. Okay, I'm going to show you what the quiver plot looks like as of now, because it's just going to be we're going to end up calling a different figure. So plt.figure, and then quiver with the arguments ex comma ey. my runtime just disconnected, so I'm going to have to, when I run this, it's going to take a second. Uh-oh. Okay, I think that it works now. So notice how gross that looks. And it's just because the vectors that are really close to the source points end up being really high magnitudes because, whenever you get closer to the source, the electric field just gets a lot higher with respect to like the points that are outside that range. So instead of just getting out the quiver naively like that, we can try and scale it down a little bit by setting a limiting magnitude for the electric field. For our purposes, 4E10 I found works. So now we're just going to run through the entire EX array and EY array by running through all the values of I and j. We can calculate the magnitude of the electric field like arrow at each of those points, again by doing the Pythagorean theorem. So this is going to be EX indexed I comma j squared plus EY indexed I comma j also squared, and we're going to calculate a ratio between that value E divided by the limiting factor that we set. And if we find that the ratio is greater than 1, then we are going to divide these particular EX, EY values by that ratio, so that when it shows up on the plot, the vector arrows are pretty much being normalized by that. Okay, let's give that a run, see how it looks. Yeah, so if you can get any information out of that graph, then good for you. The arrows are incredibly small, and it's really hard to see anything from that. And so that's why I think it's kind of silly that Newman gave us n equals 100 instead of a smaller value, like 40 per chance. One, because it's way easier to calculate n equals 40. It takes a lot less time, even though the images end up being lower fidelity. But look at that vector field. Wowee, isn't that amazing? It's just, it's beautiful. And I'm sure it'll show up great on the video in 480p. But that's part B. So now we can move on to part C, where we have to do all of this again, except instead of using point charges, we're going to be using the continuous distribution of charge given by this sigma function. So this guy is going to be kind of funky to play with. So we're going to create a different code cell. I'm going to grab some of this code though before we go anywhere. Just that bit. It's really not that much. But I'm even going to get rid of the Q constant because we don't really need it anymore. And so this is the formula that we have to try to calculate here. This phi of x and y equals that junk. The size of the box is still 1 meter. We're still going to do 40 slices instead of 100 because if we do 100 slices, it will take a day to run the code, believe me. And so we didn't even need to write this guy. The separation between the grid points is still going to be the length of the box divided by the size. We're going to create, because we have to do a couple of integrals to calculate the phi, what we're going to do is we're going to define 3 functions. The first is going to be the integrand, so def integrand, which is going to be a function of x, y, x prime, and y prime, which is going to return the charge density, the charge distribution divided by that square root thing. What is the charge distribution, you might ask? It's q naught sine of 2 pi x over L times sine of 2 pi y over L, where q naught is a constant. It's just going to end up being equal to 100. So let's just write it all out explicitly in this return line. 100 times numpy sine 2 times pi times x over L times the sine of, again, 2 times pi times y over L. But then it's the sigma of x prime and y prime in the formula for the potential, so we better specify this as x prime and then y prime here. Then it's divided by the square root of the crazy stuff, which is going to end up being x, let me put it in parentheses, x minus x prime squared plus, and then it's y minus y prime squared. And then here's going to be something that is non-physical, but we're going to have to do it anyway, because if we don't, the plot is going to look weird. I'm going to add an arbitrarily small number to the denominator. 1e minus 12, I think, is good enough. So 1e minus 12. That way, if we end up at a singularity point where x happens to be equal to x prime, and also y equals to y prime, then there's still something in the denominator, and we're not dividing by 0, we're just dividing by a really small number, right? So that's that. We're going to need to define a function which is going to do an integral with respect to x of the integrand. So I'm going to call this function int underscore x, which is going to be a function of x, y, and y prime. Doesn't need to be a function of x prime. So how we're going to do the integral? Of course, it's going to be Gaussian quadrature, and we're going to use the same value of n to do the Gaussian quadrature, because otherwise it's going to take way too long. So we're going to set up our input variables, x and w, to get the Gauss xw of n function. Again, that's from the online resources. Go and grab it, you'll need it. Xp sub x will be 0.5 times L times the x underscore x plus 0.5 times L times nothing, actually, that's it. And then Wp underscore x equals 0.5 times L times W underscore x. If my notation doesn't really make sense to you, go back and watch the video where I did a double integral before. It's just because we're taking the integral with respect to x. We're also going to have to take an integral with respect to y, so I'm doing underscore x's and underscore y's for each of those. So set up the sum, so that's going to be 0, and then 4k in range n, we will add onto the sum our wp underscore x indexed k times the integrand, specifically called x comma y comma, for x prime we put in xp underscore x indexed k, and for y prime we just put whatever y prime came into the function, and that will return the value of the integral, right? That's all fine and dandy. Now we need to find a calculation for the phi, the function I'm going to call phi calc, which is just going to take as arguments x and y. And what it's going to do is it's going to do the y integral now of the integrand, which means the y integral of the x integral. So wy equals Gauss xw n xp underscore y equals 0.5 times L times x underscore y plus 0.5 times L WP underscore Y equals 0.5 times L times WP, not WP, W underscore Y. I'm kind of losing my mind doing this code. And S equals 0, and then 4K in range N. You add on to the sum WP underscore Y times the integral, the x integral of the integrand, which is int x. And then we call x, y, and then for y prime we put in xp underscore y indexed k. Right. After all that, we return the integral, the value of the integral, so s, but then also divided by 4 times pi times epsilon naught, right? In keeping with the prefactor out in there. Okay, now let's create the output array, which again is going to be an empty numpy array of shape n plus 1, comma, n plus 1 with the float data type. Then run for I in range n plus 1, set y equal to I times a for j in range n plus 1, and then set x equal to j times a, and then you just have your phi index ij be equal to the calculated phi function called x comma y. And then after that, you can do the imshow guy again. So that's going to be just phi with vmin. You're going to use a different vmin for this one, actually. I find that it looked a little bit better for 5 times 10 to the 11 here. And then that's actually going to be max, set vmin to minus 5e11, with, again, the jet color map because it looks lovely. So if I didn't make any errors, it's going to run, and I already messed it up because this isn't called phi underscore cal, it's called phi underscore calc. And also Gauss XW is not defined because I didn't run the code cell that came from, which is this guy, again, from the online resources. Go and get this and run it before you run this, which is our beautiful scalar potential code. And now it's telling me that setting an array element with a sequence, that's not good. I shouldn't return a sequence. Oh, it's because I need to index k in here. Minor mistake. Yeah. So okay, it's done returning errors right now, which means it's actually running. What it's doing is it's running through 40 times 40, so roughly 16 times 100, so like 1600 different points, right, on the grid map. But then also on each of those grid points doing a Gaussian quadrature integral twice. So it has to do 40 points of Gaussian quadrature in x and also 40 points of Gaussian quadrature in y, which I don't even know how many points it has to go through. So my guess would be 1600 times 1600, so somewhere on the order of 10 to the 8 different calculations. So it's going to take like 3 minutes to run, I think. If you did n equals 100, like Mark Newman suggested, it probably would have taken you hours to run this code. And so doing it with 40, I think it's enough to see the scalar field the way that he's intending you to. So I'll see you when it's done. Oh shit, it finished running. Okay, so hello, welcome back everybody. It's like 9 minutes later. And yeah, okay, so that's what the uh, electric potential field actually looks like with 40 points. You can, I mean, it's not very high fidelity, again, because we only used 40 points uh, for 40 rows and 40 columns. But I think it looks pretty awesome. And we can also very easily, thank goodness, just go ahead and get the um, EX and EY plot as well, just using the same code snippet as we used before to calculate the electric field lines, um, to also display those. And I think those also look not too bad. Um, obviously the code would be more accurate if you were using 100 points, but again, it would take you like hours to run the code. So I think those are pretty good for our purposes. All right.